Let's go back to activating and deactivating groups and how they direct the synthesis when we have another substitution. So in a previous video, we talked about electron donor groups, and here I'm going to do this electron donor group. If we have an electron donor group, we're enriching in electron density the ring, we're making that a stronger nucleophile. So those react faster than benzene, which is your baseline. And important, all electron donor groups are ortho para directing. So if you're doing a nitration, for example, with something that has an electron donor here, the substitution is going to occur at the ortho and para position. So that is activating groups. Now we have other type of groups, many, except for one exception that we're going to talk about now. So electron withdrawing group, for the most part, they're going to be removing electron density from the ring, making it less reactive, and they will be meta directing. So these are deactivating and meta directing. We have two meta positions, right? So now, we said that we had one exception, and that is the halides. Let's do that. So let's analyze what we have here. Chlorobenzene. Chlorobenzene. Well, in terms of what is the effect, do they react faster or slower than benzene? So these are electron withdrawing. So they remove electron density from the ring. Because of that electron withdrawing group, they're going to be deactivating. The exception is that these groups do not direct meta. The exception is that halides, substitution, they direct ortho para. And how is that? So we have that effect, electron withdrawing effect makes it deactivating. Now, if we do resonance structures for chlorobenzene, how you would do it, if you have chlorine here, all of the lone pairs, you can draw a resonance structure like this. And in that resonance structure, and remember that chlorine can have more than 8 electrons around, so not breaking the octet rule. So here, I'm going to have the following structure. And you can continue doing that and creating negative charge at ortho and para. So in summary, let's say that you have delta negative in this position. So I'm going to do this. Now, and the chlorine positively charged. All right. What that says is then this, the whole ring, the molecule is deactivated. Yes, because that's electron withdrawing, but we will have relatively more electron density at the ortho and para position. So all of the halides do that. Now, the fact that the chlorine, for example, orients para, and that resonance is not predominant in this case, because remember that when we had, if we compare that to anisole, which we had an example. Also, there is a dipole in that direction, yes. But the electron donor effect here, plus R, is greater than the minus I effect. These two elements, oxygen and carbon, belong to the same period, second period of the periodic table. So the overlap of the p orbitals is effective, same size of the orbital. But when you're doing carbon and chlorine, chlorine is much larger, so say that that's the orbital. So that overlap that we need for the resonance is not as effective. So here, the deactivating effect minus I is greater. So yes, all of the halides, then there will be, this is the predominant effect, so minus I, but still the resonance effect explains why these groups being deactivating are ortho para directing. So summarizing, all of the electron donor groups are activating, and all of them are ortho para directing, as I have here in the arrows. And except for the halides, or electron withdrawing groups will be deactivating and meta directing. Halides are deactivating as well, but they are ortho para directing. That's something that we need to remember when we are predicting products. And now we're going to be doing a lot of problems on that. So this is like the basics, knowing what is the activating, and how they direct in synthesis.